Okay, let's make a start. I think a few more people have just popped in. So hello everyone. Welcome to this Radiant masterclass on explainable AI. My name's Professor Alan Tucker. I head the Intelligent Data Analysis Group in the Department of Computer Science at Brunel University of London. I've been working with medical AI for over 25 years. It's taken some time really to reach this point, I think, where suddenly we're seeing we could be potentially on a massive breakthrough period where AI is going to really start to transform healthcare within the UK and across the world. What I want to do today is focus on this concept of explainable AI and how regulation is starting to work with different AI and different technologies that offer different degrees of explainability. So what I want to do is firstly just tell you really what regulation is already out there that has an impact on the requirements of explanations. I then want to spend some time talking about the different technologies that are out there. So talk about the different types of explanations that can be generated from well-established AI techniques all the way up to some of the state-of-the-art approaches to trying to explain decisions. I then want to spend some time talking about trust and trustworthy AI. And what I want to do within that is describe a study that's been carried out by the MHRA and Brunel University, exploring how clinicians behave and getting some feedback from clinicians and regulators when exposed to decision making with explanations. I then want to talk a little bit about the existing guidelines that are out there within the UK and a little bit beyond as well, before performing some horizon scanning, talking about what things may actually end up impacting future regulations and guidelines that appear in the next year or two, based on some of the research papers that are out there before wrapping up. So without further ado, why do we need explainable AI? So the adoption of AI within healthcare and within any critical decision-making application requires trust, and that requires the trust of regulators, people who are actually trying to regulate some of this new technology. It requires the trust of the end users, so the clinicians or the GPs that are going to be using this technology. And probably most importantly of all, it requires the trust of the general public for them to be comfortable with this being adopted for making decisions about their healthcare journey and about their life decisions. So to require that trust, we need to have some element of transparency about decision making, especially if we start to transfer some of that decision making to technology. Now, that's fine, but the behavior of many algorithms and new technologies can be extremely complex. What we often call this is many of these algorithms and techniques black box, and we'll talk about that in a moment. They're also quite unpredictable. They're not easy to be able to predict how they'll behave in potentially new situations. So when I say black box, this is essentially, you can imagine that you have a technology that takes inputs. This can be data to train it, or it can be data that it's going to make a decision about. And you don't really know what goes on. You don't understand the internal behavior of the model. You certainly don't know how the decision that comes out the other end has been produced based on the input. And these kinds of models have certain implications. They often a black box for the reasons that they are complex and large. So they often involve huge numbers of parameters. They typically use things like weights rather than well understood statistics. So they don't work with, for example, probabilities or odds ratios. They work with these kind of more ad hoc statistics that often include and are used within the neural network family of approaches. So these are typically considered black box. Unfortunately, these types of techniques are often the most flexible and powerful, but also the most unpredictable. So trying to deal with these black box models is really fundamental if we want to generate explanations and therefore gain the trust of the population who use them. So there are already regulations out there, including in the UK. So UK GDPR already has some stipulations about generating explanations, and in particular about automated decision making. So if there is no human involvement within a decision that's been made from a technology like a piece of AI, then an individual must be able to obtain an explanation of a decision that's made about that individual so that they can potentially challenge it. That technology must also provide meaningful information about the logic involved in the decision-making process. So this is already enforced, this is already enforceable, and so that already has an impact on any decision-making that is automated. As a result of GDPR coming into force, unsurprisingly, the concept of explainable AI really took off within the research community. And you can see here the graph from 2019. It's almost vertical takeoff in terms of the number of papers that we see on interpretable machine learning and explainable AI. So what I want to do now is talk you through some of those explainable AI methods at a very layperson approach. And you can see here a list of some of the techniques that are out there. Probably the most commonly seen approach to generating what we would call an explanation is feature ranking, where a set of influential features that are used to make a decision are ranked to show which ones were most influential in a particular decision. But I also want to talk about the difference between global and individual explanations. And then I'll talk about some of these other technologies too, with some examples. So interpretable models, first of all, are models that already seem very transparent and understandable. So unlike these neural network-based approaches, which can be huge, which can involve vast numbers of weights that are very difficult to unpack, interpretable models naturally work in a very transparent way, sometimes in a way that a human may naturally think themselves. And a decision tree is a classic example of this, developed by a human, a botanist, in fact, to help humans, to help botanists make decisions and classify different plants. So it works in a very natural way, the way a human would work, trying to split up particular cases or individuals based on features about that individual. So traversing a decision tree is very natural. As well as that, there are some other techniques, Bayesian networks, which appeared in the 1990s, kind of model influences. So you have something like an influence diagram you can see on the left here, and they work with probability distributions, in fact, conditional probability distributions. But there are algorithms that allow you to visualize these networks, so you can actually see which features in your data set influence one another, and you can even enter evidence so that you can see what impact different pieces of evidence have over other features. So they're very interactive, and they think quite, and they behave in quite a transparent manner, which helps and aids the understanding of how a decision is being made. In fact, even going back to standard statistical models like logistic regression, we can do things like feature ranking, where we rank whether a particular feature is influential within a model based on training data that have been used to build that model. So all of these models are really quite transparent in how they work and quite interpretable. Having said that, whilst the parameters and structures are easily understood, sometimes the behaviors can be quite complex to follow. So for example, within a decision tree, how the features interact are not always straightforward and not always that easily explained. By the way, these three approaches and these three examples I've shown here are examples of global explanations. So they show how the model works across the entire population of data that's been used to train that model. This is very different to another type of explanation, which we could call a local explanation or individual explanation. And what this does is it answers how a model has made one specific decision. So here you can see an example that's been generated by an explainable AI called Lime. And what you can see is the output here is firstly on the left, some probabilities of a particular prediction. And you can see that it has a 0.96 probability that the prediction is positive. But then what you also have is some feature rankings. And these feature rankings show you for that individual case, what was the most influential set of features for that decision. So this particular technology, Lime, and there was another related one called SHAP, which also generates these feature rankings, actually are known as model agnostic. They work with any AI model you like. What they do is they actually learn a local model that they can then use and explain. So rather than trying to pull apart a complex model like a neural network or a deep learner, they actually build a localized model that replicates the decisions of that particular complex model. But it gives you this nice kind of visual interface to allow you to understand individual decisions that are made. Another type of explanation is known as the counterfactual. And what this does is reports a what-if scenario for a single decision. So if you imagine this figure on the left here is a population of data. So these could be individuals, each point in this plot. Some people have been classified as low risk, let's say those in the blue regions of the data space, and those who are high risk in the red regions of the data space. If someone is then classed using this model that's representing this boundary of regions within the database between high risk and low risk, if you have a model that then classifies, let's say, you as high risk of a particular disease, what a counterfactual will do is tell you what changes need to be made to your data to reclassify you. So to step over the nearest decision boundary to make you low risk. So for example, it might say, if you want to be reclassified as low risk, you must stop smoking, change your diet, etc., etc. Typically, these counterfactual explanations appear again as feature rankings, as you can see here. So for example, you can see this is actually for risk of another heart attack. The best thing you can do is not to have had a previous heart attack. So what you can see here is sometimes counterfactuals will include impossible suggestions. The next thing you might want to do is become younger. So again, another impossible thing that you can change. But then you will also see things that potentially you can make changes to that will help move you from the high risk regions of the data space to the low risk. So this is another approach to explaining an explanation of a decision that's been put forward by a model. Now, the approaches I've looked at so far are all working with structured data. So, where you may have a set of data for individual patients or individuals in a structured table. Lots of new AI models don't just work with that kind of data. They work with images and they work with text. And one important form of explanation that's put forward for image data are saliency maps or activation maps. And what they do is, again, working on individual decisions, they will highlight regions within an image that have been most influential on making that decision. So again, very similar to feature ranking, but here it's highlighting saliency within the image. So you can see here some examples on X-ray or radiograph of an elbow where different regions have lit up, which have been most influential in making a decision about abnormalities in the elbow or wrist. These clearly look like it's where attention is being made. It's not always that straightforward to interpret these, however, and the different forms of saliency map will tend to differ sometimes. So trying to understand exactly what these maps represent can sometimes be quite difficult to interpret. Nevertheless, they're quite useful in showing when a model is looking in the wrong region, and therefore the decision that's been made for that particular image may be less trustworthy. There are also a whole host of explanation approaches that work using dialogues. And we can in fact go all the way back to early expert systems in the 70s and 80s. So for example, MySyn was one of the most famous expert systems that worked with medical data, and it formalized human reasoning. So trying to understand how an expert, a clinical expert, would reason about information. And it will generate these interactive dialogues like you can see on the right there. So very much forming complex, well-formed explanations. More recently, causal modeling has been put forward as a way of trying to bridge the gap between expert systems like MySyn and models that you can learn from data, where you can infer certain relationships between features. You can also use expertise to enforce causal relationships and then generate explanations from them. And then, of course, there's a whole family of large language models which naturally create these dialogues which you can interact with to ask questions about decisions that have been made. I'm going to come back to large language models towards the end of this talk because they're kind of a special case in terms of explanations. So just to summarize, there are already a host of existing methods, all the way back to naturally interpretable models and those early expert systems like MySyn, all the way through to some of the state-of-the-art approaches like LIME, Shapley, and saliency maps. They all are suitable for different types of data, but also different types of analysis, what you want to do with them. And some may be far easier to follow than others. So they're very much the type of explanation that you want to generate will depend on the application that you're trying to work with. Okay, what I want to do now is talk about how some of those explainable AI methods have been, how they interacted with experts in different communities. So we carried out a 9-month project working with the MHRA at Brunel, where we wanted to find out some insights and recommendations from a group of healthcare professionals, regulators, patient representatives, and data scientists. This is freely available on archive here, and I put the link later on as well. But what we did was we exposed clinicians and regulators to simulated patients with decisions made by AI and their explanations. And based on that, we asked for feedback from these different groups of experts. And all of the details are in the paper. But what I'd like to do is just go over some of the key findings that we've found from that, because it's really quite pertinent, I think, to how explainable AI may well be regulated in the future. So some of the key findings, and some of these are not so surprising, is that regulators were clearly more interested in those global explanations, so those naturally interpretable models and ones that helped you visualize the entire model, so how it would behave over a population. And that compared very much to clinicians who were far more interested in those individual local explanations, wanting to see how the AI was making a decision and explaining it, and how that would compare to perhaps how they would have made a decision and explained it. They did feel that the explanations were really useful in either discounting particular AI decisions or supporting them. So we could see the impacts it would have on individual clinical confidence based on when they saw these AI decisions and explanations. Clinicians were also really impressed by counterfactuals as an approach to explaining decisions. They saw it very practical, very helpful, and mimicked exactly what they may well do themselves. So they liked seeing an AI approach to doing that. What clinicians didn't like were overly complex explanations. In fact, LIME, which is one of the kind of, if you look in the research community, LIME is seen as one of the most popular approaches. But a lot of the clinicians we spoke to didn't like the idea of solving complexity in a model by just bolting on some more technology onto the side of that model, which is kind of understandable. It doesn't really open up a black box. It just kind of, tries to explain the outside of the black box. And so they were not particularly comfortable with doing that. There were some serious issues raised by regulators and clinicians and patient groups as well, actually, with overconfidence that you see in AI making predictions. And this is commonly known, I think. It's very much related to trust, but I think it's also related to explainability. And I think reporting reliable confidence in a prediction should be considered part of an explanation. And many AI techniques do not seem to know when they don't know. So you get this illusion of confidence, and calibrating that confidence is really important. So you can see in this figure here, for example, the behavior of an AI, which is not untypical, where you have confidence is higher generally when the AI is correct, so on true negative and true positive cases, and generally lower when it's negative and false negatives and false positives. But you often get these outliers, or sometimes quite large numbers on the outer quartiles, where you have an illusion of high confidence when the AI is wrong. And I think this is really an important thing that has to be addressed by many AI models to gain that trust in end users. Some of the other comments that were made by a mixture of clinicians, regulators, and some of the patient reps as well was that it seems that humans work very differently than AI. They work with a narrative, they have some central dogma, the understanding about different medical conditions, and they use this knowledge to underpin their decision making. However, lots of the clinicians we spoke to didn't say this was necessarily a negative thing, and that the difference in approach could be seen as, rather than competing with the human, the AI could actually be complementing their decision making. What they did worry about, though, was a decrease in trust in AI if it provides lots of reasons why a clinician might be wrong. So overly critical of human decision making was seen as concerning. And I think this leads to the whole problem and the risks of automation bias. So seeing a changing workforce, which is more digitally trained and skilled with specialist roles and a tighter remit, are more at risk of things like automation bias. And I'll talk about automation bias actually in a few slides. But what was really seen as important was, just as important as generating explanations, was teaching the users when the systems would fail. So when to discount outputs. And that could simply be when the AI is not very confident. But also, obviously, an explanation that's wrong may help a clinician or an end user to say, well, it's looking in the wrong place, or it's using the wrong features, and therefore to discount that particular decision. But a nice positive thing that came from this study was that AI didn't have to be seen as somehow special and unique, and that lots of the clinicians felt comfortable with seeing it as just another tool, that it works in some situations and it may fail in others. And it's more important to know when those systems fail and understand that before they start using them, rather than understanding to a really deep level how those particular technologies work. And that's nothing new. It works the same way with plasmagraphs and ventilators. Okay, now what I'd like to do is a whirlwind tour of some of the guidance that's already out there in the UK that has some relevance to explainability and the concepts of explainability. Starting off with guidelines, some guidance that was put out in 2023 as part of the change programme roadmap. And what you can see within the text within that guidance was a lot of the use of the word transparency, and transparency comes up a lot, and sometimes transparency directly reflects to, links to explainability. Sometimes more it's actually about being transparent about the intended user population or the data that's been used to train a model, and these kinds of things. However, within that original guidance, there was this idea of a description of how uninterpretable AI may impact the performance of a human AI team working together. So if you don't have detailed enough explanation, then that will potentially work against the team. So I think this idea of a human AI team is a really important one. So not just treating the performance of the AI alone or the humans alone working together is really seen as potentially the way forward here. If we look at some more guidance that was put out the following year in 2024, specifically on transparency for machine learning enabled medical devices, a lot of this was focused on transparency of processes, of the data, and the concepts of reproducibility of any experiments and analyses of technology. A lot of it refers to the good machine learning practice documents that were put out in conjunction with the FDA and Health Canada. And this document goes back to 2021, but it includes a lot of quite relevant stuff to explainability. So you can see I've highlighted in red here this idea that user interface interpretation and clinical workflow integration of the model is really important. So it's really important to have access to clear, relevant information about how an interface will interact with the human. But also, again, this idea of having a human in the loop. So you can see where the model has a human in the loop, human factors, considerations, and human interpretability of the model outputs must be addressed. So the human AI team is really important. In fact, we're starting to see already in research that's coming through. This came out towards the end of last year, a study in Poland where endoscopists were being seen to be de-skilled themselves after working with AI in colonoscopy. So what they found was the overall human AI team worked as well or better than the humans by themselves, but that over time we saw the humans became less and less skillful in detecting certain conditions, whereas the AI was kind of stepping in. And that could be a potential concern. This is a classic example of automation bias that may well impact guidance in the future. In fact, automation bias has been flagged up for many years. The impacts not just of an AI working by itself, whether it's better or not than a human, but the societal and the human factors of a human working with an AI. And I think this cartoon tells it quite neatly. This idea that if a human is working and is in the loop, it isn't just a get out clause, because having a human in the loop with a really highly predictive 99.9% accurate piece of AI can have all sorts of destabilizing impacts on decisions that are made in terms of liability, for example. So if a human disagrees with the AI, they're seen as liable for that decision. Whereas if they agree with the AI and they both get it wrong, then it's a system error. So there is this kind of the human factors that are really important to take into account and almost certainly will impact guidance in the future. Some more work that's been going on in the MHRA are the airlocks. And these have touched several times on explainability. In fact, in the first round airlock, there was a case study working with OncoFlow, specifically looking at explainability approaches, looking at interpretability and transparency. And that report is available already at this link. I do recommend you read that. It's really quite interesting seeing how OncoFlow are dealing with some of these things. Beyond our shores, obviously everyone knows about the EU AI Act. This has got some work on explainability, an awful lot of stuff on trust. I've pulled out some key points on explainability here, and how high-risk AI systems and decision-making in healthcare is clearly would fall under a high-risk AI system. You can see here some of the things. So I've highlighted at the bottom, where applicable, the high-risk AI system must disclose its technical capabilities and features that enable it to provide information relevant for explaining its outputs. So explainability is really fundamental here. And there's other mentions of transparency and explainability in these other sections too. So it's not something we can avoid. Explainability is fundamental to trust in AI systems, particularly in critical decision making. What I'd like to do now is just a little bit of horizon scanning, because UK regulations are still on the horizon, and the sorts of things that may be influencing those I want to talk about a little bit now. I also want to come back to large language models, they clearly look like they're generating explanations when making decisions, and talk a little bit more about some other related research. So, actually, I wrote this slide last year. It could be this year, the UK general AI regulations. They're coming. They were delayed. It's going to be a comprehensive bill. We don't know exactly how it will compare to, for example, FDA or to the EU AI Act, but it is coming. In the meantime, we do have other things happening that can be explored to kind of get a feel of what's going to be in some of those regulations. In particular, there were blueprints and action plans that came out last year, but also the setting up of this UK National Commission on the Regulation of AI in Healthcare. I put some links to some of these here. One thing to point out is explainability hasn't been pulled out explicitly in the National Commission, but trust has. Trust clearly will involve some element of explainability and transparency, as you can see in those earlier guidelines from the MHRA. So watch this space on that. Now what I want to do is just talk a little bit about LLMs. There is quite a debate going on in the UK amongst the research community and within regulators too about the use of large language models. Clearly, we're seeing them slowly being used within healthcare services around the world, for example, for scribes. In terms of decision making, but also actually within scribes, there's known issues with things like hallucinations and omissions. The paper I've put a small excerpt from in the bottom right is particularly harsh on the use of LLMs for any serious decision making, rejecting the idea of using even terms like hallucination and lying as metaphors, and claiming that an LLM is indifferent to truth and is actually been trained and built to convince a user rather than to actually put forward what it thinks is the truth. So there's no real underlying understanding. And these kinds of mistakes and using these kind of terms like hallucination and lying is highlighted in the paper as major implications for public understanding and policy, because these terms can lead to a misunderstanding of the capabilities of AI like LLMs. There are also, of course, other more nuanced, I would say, publications about LLMs and explanations. There's a group at Oxford led by Sandra Vactor who've been doing a lot of work about the relationship between LLMs and reasoning and the truth, which are well worth exploring. Within our group at Brunel University, we've had a team looking at different reasoning tasks using LLMs, and there's a nice survey that's now just come out as a preprint that's available with this DOI here. It's not on arXiv because arXiv doesn't accept surveys anymore. But if you need more details about accessing this, do let me know. It covers many different types of issues with LLMs, including some of the impacts of the mistakes that LLMs can make, but also potential ways of getting around some of those issues. In fact, the regulators are already quite aware of some of these issues. All the way back to 2023, there were case studies of large language models in this policy paper here. What they highlighted was the potential really for issue-specific guidance and requirements for LLM developers and deployers to mitigate some of the risks that are seen there. So it's worth looking at this white paper too if you're working with LLMs, because this could well impact some of the regulations that come. Okay, some other interesting stuff in the research, and I think this could also have impact on explainable AI in general, is this idea that if an explanation is given for a decision, and we saw earlier in that Brunel MHRA study that it can help an expert discount a particular decision if the explanation is wrong. And that's fine. In fact, I put this rather strange figure up here of leopards and killer whales because there is a nice paper, if you want to skim through with a link here, that shows that you can generate an AI trained on some image data here to perfectly classify leopards from orcas, from killer whales. But then if you generate the explanations, what you see is it's getting it right almost every time, but the explanation is wrong every time. And that's because it's just focusing on the background. So if there's lots of blue water type backgrounds, it's a killer whale. If there's leaves and greenery, it's a leopard. So it's getting the decisions right, but the explanation is wrong. And that may well have implications in the longer term if clinicians are being fed false explanations and this isn't being detected because the decisions are correct. Probably even worse than that, though, is when you have an incorrect decision made by some AI, but the explanation is convincing. And we do see that with LLMs, but also with some of the traditional AI approaches too. In fact, in our pilot study that we carried out, that's in that archive paper, we demonstrate some individual cases where clinicians were convinced to change their decisions, but to an incorrect decision because of the explanation from the AI. And I think the idea of a false explanation is an important one to take into account. So just providing an explanation, which is being put forward by regulators at the moment, may not be enough because it may produce new dangers that we need to be aware of. So this is something that may well be discussed in the future. So just to wrap up some of the case studies, and these are mostly ones that I talked about earlier. So if you want to go and see some case studies of explainability within the AI community, Oncoflow within that first phase of airlock is a really interesting one to read about in their report. There are also some other case studies in the second phase of airlock, which will be reporting in March. One of them very much is focused on explainability. The other touches upon it. So do look out for that. Within the RADIANT-CERSI, we have a regulatory journey support project ongoing with Ingenium, looking specifically at explainability. So once those the reports from those come out, it will be worth looking at too. We are also within Radiant extending some of the studies we've done already on explainability and trust. We have a questionnaire available for healthcare users. You can see the link, that second link there. So if you have anyone working as clinicians, do spread the word about taking that. It essentially exposes them to some simulated patients, some decisions made by AI along with their explanations, and ask for feedback from that. So do watch this space within the RADIANT-CERSI. Look out as well for some of those reports coming from the airlock, and follow the National Commission on AI regulation too. Okay, that's everything I wanted to say now. Of course, I'm open to any questions here now, but also my email address is here if people want to ask me questions for follow-up. I can also point you to the right people within Radiant and so on, should you need any sort of clarifications. Thank you very much.